Hello guys, welcome back to a new tutorial. Hope you are enjoying this series and learn a lot from these videos. In today's video, we are going to analyze flow through a butterfly valve, in which we will see the impact of sand on the valve, that how the sand can be eroded the butterfly valve, and let's see the problem overview. So first of all, if we talk about the purpose of the simulation, we want to see the flow pattern, the flow behavior around the valve. Also, we want to study out the head losses in the valve. Also, we will see some of the techniques that at which angle the losses are minimum and there is no erosion on the butterfly valve. Also, if we talk about the boundary conditions, the valve has a diameter of 20 mm, that is in a radius, sorry, not diameter, and the flow from the inlet is 5 meter per second. We have placed the valve at 55 degrees. Also, about the sand particles, the diameter of the particles are 50 to 500 microns, and the roughness of the valve is 0.2 mm. If we talk about the flow behavior, the flow is fully developed because we are not taking the complete pipe, we are taking a section of the pipe, so we consider that the flow is already developed. You can see check this terminology in fluid dynamics, that what is fully developed flow and what is underdeveloped flow and what is boundary layer. What's new in this simulation is basically we will study out fully coupled simulation and one-way coupled simulation, that how the fully coupled flow behavior of the erosion and how we can treat the erosion particle in one-way coupled simulation. So in short, what we are going to learn, we will see how to create roughness wall, we will see how to define the fully developed flow, we will see how to do the particle tracking simulation and how to get results, and we will also see some of the quantitative pressure calculations, like how we can calculate the pressure losses in the pipe using the function command in the CFD post. So let's start. Let me delete the system. Okay, drop the CFX system from the toolbox. Now we have to import our mesh. I will provide the source file in the drive, so you can download it from there. Okay, the mesh is updated. Now come to setup. Delete the default domain. First of all, come to material, create a new material, and come to material properties. See, the density is 2300. Specific heat capacity is 0 because we are not studying the thermodynamic effect in this tutorial. Also, the reference date, I am taking it 2500, 25 degree, or 1 second, it is 300 Kelvin. It does not matter because it is just a value to be given, that has to be given to the software, because we are not studying the thermodynamic effects in this video. Okay, so material is being defined. Now come to the domains, insert a new fluid. सारा इधर से भी काटना है. Okay, now the material is defined. Now we have to insert a domain, fluid, click on location. There is only one domain in our current scenario. Now come to this domain type, that is fluid domain. Delete the default material, create a new material naming the water, select the material. Now define a new material, that is sand one way. That is not a fluid. I also select the material from here, it is sand. We will choose particle transport solid. Okay, it's fine. And we will take normal in diameter by mass. Now we have to define the diameters. I am changing the units to microns. Okay. Minimum diameter is 50, maximum is 500, and the average is 250. Again, let me change the units to okay. And the standard deviation, let we see in the document, the standard deviation is 70. Okay, so we have defined the material properties. Now again define a new material, particle two-way coupling. Select the same material, sand, particle transport solid, particle mean diameter, the same boundary conditions that we have taken earlier. Okay, it's fine. Now come to fluid models. Turn off the heat transfer, change it to K epsilon. Now come to fluid specific models. I am going to use the Erosion model. Come here and see reference velocity is 1 and velocity power factor is 2 for both of the systems. Also in fluid pair models, we have to select fully coupled for particle two-way, and for one way we have to select one-way coupling. Also for the drag, I am using the default drag mathematical model. All done here. Now we have to click on OK. Now insert a boundary condition and let specify the velocity. That is maximum velocity, but we have to define it with the equation. So let me close this and come to the expressions tab. Insert R max, that is 20 mm. Click on apply. create a new expression, copy the W max, paste, it is 5 meter per second. Click on apply. Now we have to create the final expression, W flow, click OK, select the expression, okay, click on apply. We have seen an error here, so it's not taking these expressions. Also from here we have to select our max. Now again click on apply. It's giving syntax error again. Click on OK. Let me rewrite it manually. Expression flow multiply we will take absolute function and have to define 1 minus r divided by r max, and then we have to take the square root. All done. One second. Syntax error detected in assign 6 value 8. So if you so there is only a simple error we are not seeing is the bracket. Click on apply. We have done. Now come to outline again, insert a boundary condition, inlet, click OK. So we have to change the normal velocity, Cartesian velocity component. In the u direction the velocity is 0, in the v direction the velocity is 0, in the w direction the velocity will be governed with the equation. So come to fluid values, define particle behavior, same method, Cartesian component, okay. In the number of position, for fully coupled we have to place the particle count of 200, and for one way we have to take the particle count of 5000. So it is two way. The number of particles will be 200, mass flow rate is 0.01, and for sand one way, again the Cartesian component, is 5000 and 0.01. Let me verify it again. Is the flow rate. Click OK. Create a new boundary. Outlet. Zero relative pressure. Click OK. Insert a new boundary. Symmetry. OK. Now we have to define a rough wall. Insert wall. Pipe wall. Boundary details. It is no slip and a rough wall. The roughness is defined 0.2 mm. Change the unit to mm. Also, we have to change this perpendicular coefficient to 0.8 and parallel coefficient to 1. Also for fluid 2. Okay, click OK. Now we have to see the particle effect. We have to default boundary. Here it is, and we can see we first of all basically it's 0.9. Click OK. Click OK. Okay, all of the boundary conditions are defined. Now come to solver setting. Change okay, the 100 iterations are fine and minimum iteration set to 10. Also change the target residual to 6, and also you want to make it 300. Okay, so it's fine. Now we have to change do some changes in the particle control. Come to particle integration. Okay, and the maximum particle integration time step is 1. Tracking time, maximum tracking time is 10. Second. Okay. Also maximum tracking distance is 10 meter, and maximum number integration steps are 1000. Okay, all done from here. Click OK. So we have done the setting. Now we have to define the initial conditions. Make it Cartesian, automatic with value, and that's the Click on OK. Close this window. Bench. Double click on solution. Click on double precision. Initial conditions and start run. Okay guys, the simulation is completed. We get the converged solution in 100 iterations. So let's close this window and now come to results. So now we want to see the one-way and two-way coupling. So what is one-way coupling and what is two-way coupling? Basically, one-way coupling. In one-way coupling, we what we study that the particles of the sand does not affect the flow pattern. If we speak in the technical background, what happened in one-way coupling simulation? The software run a simulation without considering the particles that are present in the fluid. The software just consider the flow behavior, and once the solution is obtained on the flow behavior, then the particles follow that pattern of the flow, and then we calculate the erosion. But in two-way coupling, the effect of the erosion particle, I mean the sand particle, has been considered, and the fluid flow and the particle flow are, you can say, in interaction with each other has been solved. So basically the effect of sand particles that are present in the water will be considered in the two-way coupling. That's why it's called two-way, because it's interaction of fluid to solid and solid to fluid. But in one-way coupling, only solid will interact with the fluid, but fluid will not interact with the solid. That's why it's called one-way coupling, and the second one is called two-way coupling. So let's get some results. Let me plot a contour on default fluid. Click apply. So we can see the pressure effect. Let me change it to 50 contours. Okay, duplicate it. But okay, view, apply reflection about YZ axis. Click apply. So we can see the identical results. Now I want to see in the two-way coupling, I want to see this thing, erosion rate. Click on apply. Also range has to be user specified. Click on apply, or you can make it 20 or 100. So it's up to you in which range you want to see the results. Similarly, we have to change it from particle two-way coupling, user specified, and 25. click apply. So now you can see the erosion. It's showing that most of the part, sorry, it's showing the results on the surface, like where there will be more chances of erosion. So basically wall will dissolve in the water from these surfaces fastly in compared to the blue surface. Now again come to contour, and now we have to see okay. Now we will see the particle track. Come to this particle track option, click OK. There are two, you can see there are two options. One is sand one way and particle two way coupling. If I click on sand one way, click apply. Let me change the color to okay. Create a new particle track. So you can see the difference between the lines that, so both of the solutions are not similar. If I change the color to red, so you can see. Also let me change this color because it's not that prominent with the white background. So now you can see that the flow pattern is different for one way and two way coupling. There is a small difference between both of the particle tracks. So let me edit the particle track 2. I want to see mean particle diameter. So you can see here, and I want to make it user specified to 50 microns to, let me say, 500 microns. That was, so you can see the results. Let me create a simulation, let me create a animation particle track 2. We come to the options. I want to use a 3D arrow instead of using a wall. Click OK. It's very fast. Let me make it a little slow. Also come to the option, change the size to 3. Now click again on OK. So here is the animation. If we want to create the animation about the symmetry 2. So click on particle track again, particle 3 view, apply reflection about YZ axis, click on apply. Now again come to this animation tab, select particle track 1 and particle track 2, click apply. So now you can see the flow pattern in the complete pipe. Click on options, make it 2, click OK. Now let's come to the last thing that we are going to learn in this tutorial. We can see the pressure loss very easily. We just have to create the expression head loss, click OK. Mass flow average of what we want to see. We have to select we have to select the pressure variable at the inlet, copy, minus at the outlet, click on apply. So basically what we have done, we have minus the inlet pressure from the outlet pressure. So basically the pressure difference between the inlet and the outlet provide us the head loss, that is 33,768.5 Pascal. You can also use some of the other functions, like I can use area average. So I want what I want to see the area average of pressure at what location. I want to see it at inlet. Now I want to see the difference in the pressure at the inlet and the outlet. So now I'm calculating the head loss with the area average. So there is a little difference by mass flow average and area average. These are two techniques we can use to calculate the head loss. Thanks guys, hope you enjoyed the video. See you in the next tutorial.